Good morning, all of you. My name is Moumita Ghosh. Presently, I am working as Assistant Professor in the Department of Information Technology of Haldia Institute of Technology. Today, I am going to present the topic classification algorithm. And of about classification algorithm, I am going to present naive-Bayes algorithm. Before that, we have to know what do you mean by classification algorithm. Now, classification is a supervised machine learning technique used to categorize data into predefined classes. Now, as we seen from the snippet of the dataset that it contains several features. Here the features are by, win and urgent. And the label is the we have to detect one particular message is a spam message or not. That means here we can see from the table that we have two types of label. One is yes, another one is the true. That means the problem is the binary classification problem. As we seen in the second point, the goal of a classification algorithm is to learn a mapping function from input features to output label using a label dataset. That means using these features, we have to learn one mapping function, or we have to apply one mapping function so that one features can map into a particular output labels. Now, when we do this procedure, we used to do this procedure in the training level or in the during the training session. Now, in the training session, the algorithm analyzes the input data and their corresponding labels to identify the patterns or relationship. That means one thing is very clear, that we have to bind, or bind means we have some mapping function that should be bind from the a set of input features to the corresponding output labels. Once we able to do that, that means we have our mapping function. Once we are getting our mapping function, it is very easy in the testing phase that whenever the model can predict the new of unseen data. That means in during the training session or during the testing session, it is very easy that we can detect the level of any unseen data. There are several common example of the classification tasks. The very basic or very these are the all are the very basic example, like the spam email detection, sentiment analysis, or image recognition. That means why we can distinguish between the cats from the dogs, like that. So in today's session, we will be in depth, we will be detecting the spam email using the naive-Bayes algorithm. Now, not only the naive-Bayes, there are several classification algorithms are present over there. These are the logistic regression, decision trees, support vector machines, naive-Bayes, KNN, K nearest neighbor, neural networks, and ensemble methods. Now, ensemble, now we can discuss one by one, but in today's session, we are start with the naive-Bayes. Now, as we are going to discuss only the naive-Bayes, so uh, the naive-Bayes is a very basic algorithms which is based on the Bayes theorem. Now, why now one particular classification algorithm, how it is evaluated? The performance of a classification algorithms is typically evaluated using matrices like accuracy, precision, recall, F1 score, and ROC and AUC. Choosing the right algorithm depends on the dataset size, nature, complexity, interpretability, and computational requirements. That means, as we have the several charts over here, so using the several we have some criteria also. So based on the criteria, we can select one particular algorithm. Now we are start today's algorithm, which is the naive-Bayes. Now, before starting the uh, what is inside of the naive-Bayes algorithm, it is better to know the overview of the naive-Bayes algorithm. The naive-Bayes algorithm is nothing but a very probabilistic classifier which is based on a Bayes theorem. Now, what is Bayes theorem? That will be discussed in the next slide. Before that, it is actually calculates the posterior probability of a class given the feature value. it assumes that the features are conditionally independent given that class. That means, as if we have several features in the name-based algorithm, we assume that there is no interdependency between two features or between among the features. So that is conditionally independent in between the features or among the features. This conditional independence makes the algorithm naive. That's why the name of the algorithm is nothing but naive Bayes. Next slide. There are generally three types of naive Bayes algorithm. The types are Gaussian naive Bayes, multinomial naive Bayes, and Bernoulli naive Bayes. Now, based on the features, this categorization has been made. Now, if the feature types are continuous, like what is the use cases of, so like we can distinguish some medical diagnosis, or we can predict some weather, or it could be give a hunch of a finance position of a year, or of the yearly or weekly, like that. So whenever we can find the values are numerical and it follows the Gaussian distribution, and as well as not only numerical but also the feature is continuous, we can apply the Gaussian naive Bayes. So what are the use cases of that? As we have already said, we can diagnose, we can detect some medical diagnosis or weather prediction, like that. Now the second one is the multinomial naive Bayes. Now when the values are discrete, that means it could be a categorical or not categorical, but the values should be discrete. That means there is a number of values should be present, and it could be represented as a discrete number. In these particular cases, we can use the multinomial naive Bayes algorithm. Now, the best use cases of this category of the naive Bayes is the text classification and the spam detection. And another one is the Bernoulli naive Bayes. Now, in the Bernoulli naive Bayes, the features is in the 0, 1. That means it could be the present, could be present, or feature could be present, or feature is not present. That means one feature feature type is either 0 or 1. So before going to the deep into the naive Bayes algorithm, we have to learn what is Bayes theorem. Now, in the Bayes theorem, we have some terminology. The first term is the Bayes probability is called the posterior probability, and it is written as probability of class C given on features X. And this term is the nothing but the likelihood. And P of C is called the prior probability, and P of X is nothing but a evidence. Now, how to apply this Bayes theorem to solve any naive Bayes problem, we will be see it shortly. Now, in the next slide, we have where is the position where we use the naive Bayes algorithm. Suppose you just consider a situation that you are an administrator of an email service, and your goal is to keep your user inboxes clean from annoying spam messages. However, distinguish between important emails and the spam is not a very easy task for you. So, as some spam emails are cleverly written, so it looks legitimate. So, how you can distinguish between these two services? That means you have to detect the spam message as well as the normal legitimate message. So better if you could apply one machine learning algorithm or any classification algorithm, so the which can detect or which can distinguish between a spam messages or spam email as well as a not spam or any legitimate message, then your task will be easy. So to implement such a situation, or to implement this kind of problem, we can use the naive Bayes algorithm. Let's suppose one information is provided over here. Suppose one email contains certain keywords like buy, win, and urgent. And you have noticed that spam emails often use these aggressive marketing terms like win, buy now, big offer, urgent offer, like that. And on the other hand, legitimate emails might contain some of these words too, but it will use some any other context also. Now imagine a new email arrives, which will say that the word that it will contains the word by, it will containing the word urgent, and it will contain the word will. So what will be your task? That means your task means what will be the task of the naive-Bayes algorithm. Now naive-Bayes algorithm runs in the backend so that when one such new message will be coming, it will distinguish or it will classify whether the message is the spam message or it is a legitimate message. Next. So we have taken a very small data set where we have only the 4 email IDs or emails are present, and one such email, one email contains only we assume that the email body is containing the 3 words by, win, and urgent. And by, in the by we have this is the binary class classification problem, as we have to detect whether the message is the spam message or this is the not spam message. And the keywords containing by, win, and the urgent, it could be either the by keyword is present within the email body, or the by word is not present within the email body. So if the feature is present within the email body, it is represented as yes, and if the feature is not present within the email body, it is represented as a no. Similarly, for the other two features are the win and the urgent. Here also, if win is present in the email body, it is represented as yes. And if win is not present in the email body, it is represented as the no. So if this is our data set, and what is our task? From the data set, we have to learn one mapping function, so that whenever a new mail will be coming with this containing these 3 keywords, and we have to classify whether the new message is the spam message or not. Suppose the new message is containing by, it will contain the keyword win, and it will contain the message as a urgent. So if these 3 features value is also yes, yes, and yes, then what is the probability of the message is being spam, or what is the probability the message is not being a spam message? Now let's solve the particular example using the naive-Bayes algorithm. Now, what is the first step? First step is that we have to calculate the priors. Prior means P of C. That means the class. Now, we know we have the 2 class classification problem. So, we have the only 2 values. Either it could be yes or it could be no. That means the message could be spam message, or message is not a spam message. So, let's see from the data labels that we have four different two different classes. The numbers are 4. Either it could be yes, so there is 2 numbers are present for the yes, and 2 numbers are voted for the class no. So if the message, what is the probability of a message being spam? That means spam emails by total number of emails. So we know we have total 4 number of emails. So the denominator is always 4, and as the spam messages is 2, and that's why this is 2 by 4. This is nothing but 0.5. So initially, this is the probability of a message is being predicted as a spam message is 0.5. That means the probability is 0.5. Similarly, what is the starting probability, or what is the prior probability? So a message is or email is a not spam. So that one particular email is not spam, the probability is the again 2 by 4, because we have seen that there is 2 no classes. That means 2 messages are present over here, which is not predicted as a spam message initially. That's why it is nothing but again 2 by 4. So that is 0.5. Next we have to calculate the likelihoods. Now likelihood means for each feature we have to calculate the likelihoods value. Now for the feature by, now again for the feature by we have the two features value, either it is yes or it is no. So first, probability of the buy is yes, condition on the spam. That means the message or the email is spam. And when the buy is yes, then what is the probability? So yes for buy in spam, we can see from the first tuple that where the buy is yes as well as the spam label is also yes. So that's why yes for buy in spam is 1. And what is the total number of spams emails are present? Now this is 2. That's why the probability is 1 by 2. Now see, the probability is again 0.5. Similarly, when the probability buy equals to yes and provided this is the not spam. Now what is the value? Now yes for the buy in not spam, it is the 1 by total not spam email is the 2. Now see, from the probability the buy the buy is yes. Now see here, the buy is yes for the third tuple and the spam label is the no. So that's why the probability is again 1 by 2, which is 0.5. Similarly, we have calculated these two probability value also. Now when buy is no and the spam and the message is the spam. Now for this category, this tuple, the spam is yes and the buy is no. Again, the probability is 0.5, and similarly buy is no and provided not spam. Now here also we have the probability that the buy is no as well as there is the no spam message, and this is the case for the 2. So there is total 2 number of cases where the probabilities values on the not spam value is the 2, and this is the one such case where this is probability the message is not spam, but provided that the buy is also a no condition. That's why this is 1 by 2. This is nothing but the 0.5. Same way, we have calculated the other likelihoods of the another features. Now, if we calculate for the win also, we will getting these are the values. Now, where also we have the value is for the win in the spam message like 2 by 2 by equals to 1. Why? Because see, in the win condition, this is yes, spam is yes. This is yes, spam is yes. That means there are 2 out of 2 cases present where when the mail is spam as well as the win condition is also yes. And similarly, we have calculated the probability for the win equals to no and the win equals to when provided the not spam. Similarly, all the likelihood probability for the feature win has been calculated. To the same procedure for the urgent. Now for the feature urgent, we have calculated this probability using the same logic. If you concentrate any one feature, you can easily do these things also. But you have noticed one thing, that individually we are calculating each probability value, each feature's probability value. What does it mean? It means that one particular feature is independent of another particular features. That means features are totally independent in nature. There is no interdependency among the features. Now let's calculate the posterior probability. Posterior probability means using the posterior probability we will get our answer. Now what is our questions? If I remember that in the 3 conditions we have the yes. That means our buy is yes as well as win is yes as well as the urgent the feature this is also yes. That means one particular mail is containing these 3 terms. Now that's why what is the probability the message is being spam? That's why this is nothing but probability of buy is yes, win is yes as well as the urgent is yes, and we have calculated the probability value. This is nothing but 0.5 into 1 into 1 into 0.5, and the value is 0.25. Similarly, if as the calculated value for the not spam is value is the 0. So from this table we can see that what is our classification result? The message is spam or not? As we are getting the greater value in the class of the spam category, that's why the message is predicted as a spam message. That means one such, though this is a very toy example, so that means that if the message containing the 3 words, that means spam, win as well as the buy, so this urgent. So that means say if the message is containing win, urgent or buy, these three keywords are present in a message, that means this is classified as a spam message. Now, so this is predicted like so. Now, what is the drawback? Main drawback of a zero probability naive Bayes problem means main drawback of a naive Bayes is the if one's probability goes the zero. As we have seen in the earlier case, the last category, the when we are calculating the message as a not spam, the probability goes down to 0. Why? Because suppose in a naive Bayes, the probability of a class given the features is calculated using the product of conditional probabilities of the feature. If any one of these probability is turns to 0, the entire products becomes 0 regardless of the probability of the other feature. That means if one feature is going to put a value 0, another features will not affect it as. That's why this issue arises when a feature value has not been observed in the training dataset for a given class. So this is a very severe problem. Now, how to avoid this problem, or what is the solution to solve this problem? Now, before going to discuss, suppose one such condition you just assume that imagine we are classifying emails as a spam or not spam, and the training dataset has no spam emails containing the word win. Let's assume for a new email with the win, the probability win condition on the spam equals to 0, which makes the probability of the spam based on the features equals to 0, because another features will be in no use even if the other features strongly suggest it is a spam message. That means somehow we have to avoid such conditions, or somehow we have to do something so that one particular probability value should not be 0 anytime. So one such solution is called the additive smoothing. What does it mean? To address this issue, we adjust the probabilities to ensure no probability is exactly 0 by adding a small positive constant k to all frequently counts. This approach is known as the additive smoothing. Now, how to count? Suppose this is a formula for the additive smoothing. Now, this is nothing but P of xi condition on y. That means count of xi in class y plus k, and by total count of all features in class y plus k into v. Now, where k is the smoothing parameter, typically the value equals to 1, and v is the number of unique values the feature can take. Suppose so that's all about naive Bayes algorithm. In the next session, we will be discussing the Bayesian belief network, where actually we consider the dependency among the features. So thank you.